Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 6.4 from your textbook, which looks at another application of integration. In the previous couple sections, section 6.2 and 6.3, we've been investigating how integration, specifically definite integration, can be used to handle volumes when we're looking at a solid of revolution. Here, we're going to change gears a little bit and see how definite integration can be used to answer some questions that relate to a physics concept known as work. Now, because some of you guys probably have more familiarity with work as opposed to other people, some of you might need to take more physics classes after this one. Our sort of investigation into work is going to be just a very sort of surface level here. Really, this is a concept that, while it is a nice application of integration, really is a concept that should be covered in a physics class, not necessarily completely in a math class. So for us, we're going to really restrict our attention to examining this idea of work in a very sort of limited sense. Specifically, we're going to basically be studying the work that is necessary to lift different objects of different weights, different distances. And there are many other applications of work in physics than just lifting things, but we're going to basically focus exclusively on that type of work. In your textbook, you'll see some mentions also of work done by things like springs and a famous sort of mathematical or mathematics/physics theorem, which is called Hooke's law. We're not going to be covering any of that. We're just going to be focusing on the work done to lift objects of different weights, different heights. So let's get into sort of our investigation here. We'll lay down some of the fundamentals from physics, and then we'll see how integration can sort of help us here. So from basic physics, we have the sort of following idea. If you have a constant force, F, applied along a path of length d, then the work done is calculated by simply taking the force times the distance. Now, for some of you, if you've taken a little bit more physics, you probably know that this formula here, force times distance, right, this can be sort of extended a little bit in case the force is not directly applied along the path. If it's applied along an angle, you can change this formula more generally into the work equals the force times the distance times the cosine of the angle. We're not going to worry about any of that. We're just going to be focusing on where we have a force applied directly along a path of length d. The sort of limitation of this formula, of course, which is what integration is going to help us overcome, is that this formula basically only works when you have a constant force applied along an entire path of length d. So if the force that you're applying changes over the path, this formula isn't going to apply. And if you have different pieces of whatever you're sort of lifting or moving that need to travel different distances, this formula isn't going to apply. This formula only applies when you have a constant force applied along a single path. A little bit about units. Again, as a math class, we're not going to worry too much about units. That's more the domain of like a physics class and being very careful about those sort of things. But just as a little bit of information, if you measure the force in newtons and the distance in meters, then the traditional unit for work would be joules, while if you measure the force in pounds and the distance in feet, the work would be measured in this very weird unit called foot-pounds. In a physics class, we'd have to be very careful about maybe, getting units that are not in these standard units and having to do unit conversions and things like that. I just want you guys to know that for any questions that you're going to see on like a quiz or an exam, you're not going to have to worry about any sort of unit conversions. For any question I write, either everything's going to be in newtons and meters, so you just put those two together, or everything's going to be in pounds and feet, and you just put those two together. We're really not interested in having to do a bunch of unit conversion. The same cannot necessarily be said of all the examples or textbook problems, so just be aware if you're working on some of the ones from the textbook, you might have to do a few more unit conversions than we would do it in our class or in our assessments. All right, to get a sense of just what this formula is and the sort of very limited situation in which this basic formula applies, let's look at a basic example here. So let's suppose that there's an object and we're going to consider it as a point mass. So in other words, it's all just considered as a single point that has this weight. And we know that it weighs 10 pounds sitting on the ground, and we want to determine the work necessary to lift this object straight up 5 feet in the air. So very simple here, right? If we just were to sort of draw out this diagram, there's our person who's trying to lift this thing. There's our point mass, right? This is the thing that we're trying to lift up. We know that this is a total of 10 pounds, and we are trying to take this thing and move it up maybe up to here. And we know that this is a distance of 5 feet, and we're trying to lift it from this base all the way up to there. So notice that this thing here, well, it is a constant weight. Weight is a very basic example of force. There are many other forces out there, but weight is an example of force. However much something weighs is equivalent to the force that is needed to lift it up. So we know that this guy is a constant force because it has a constant weight. And this entire object, considering that we're just treating it as a single point, needs to move that 5 feet. So the work here would be very simple. The work would be equal to that force times the distance. So the work here would be equal to the 10 pounds of force necessary, and the entire object needs to go that 5 feet, that direction. So that's 5 feet there. So the work here would be those 50 foot-pounds, just by multiplying that 10 and 5. Okay, so this is just to make sure that we understand the basic thing that this sort of physics formula applies to. What we're going to now investigate in the next couple examples we're going to be looking at are some modifications to this, where this basic formula is no longer going to be sufficient, and we're going to have to introduce some mathematical concepts, namely integration, that allow us to sort of handle this. So let's look at these examples. I've sort of given them not an official name, but sort of a nickname to help you guys sort of understand what we're sort of changing in each of these examples. So our first example is going to be what I would call the quote-unquote changing distance modification for work. Like we said back here, in this example, right, this basic formula works if you have a constant force that is applied along the entire length of the path. Now we're going to sort of take a look at where some of the distances might be changing. So let's take a look at this. So we've got this example here, and we're going to suppose that there is a rope that is 30 feet long, and the rope weighs 10 pounds. We're going to suppose that the top of the rope is attached to the top of a well. Attached to the bottom of the rope is a bucket. The bucket weighs 2 pounds, and it has water inside, and we're going to consider the bucket and water all as a single point mass, and that weighs 15 pounds. We want to determine the work necessary to lift the bucket, rope, and water out of the well. So let's go ahead and draw ourselves a diagram and then talk a little bit about how we're going to analyze this. So we can sort of imagine maybe this is our sort of well, right, like that. What we have is we've got this 30-foot rope that is going all the way down here. Then at the bottom, we have this single point, right? Now this single point is both the bucket and the water, but I'm just going to keep those separate for right now. So down here, we've got the 2-pound bucket, and just for ease, we can use a little bit of color. And we also know we have 15 pounds of water. All of that is being treated as a single point mass down here. We could just call it 17 pounds if we wanted to, but I want to try to keep things in as many pieces as sort of possible here, so the pieces are as simple as possible. And we know that this distance overall from here to here is 30 feet. And we also know, maybe not a great spot to label on it, but we'll just sort of keep this off to the side here. We sort of know rope weighs 10 pounds overall. Okay, so there's sort of all their information, right? There's our sort of 30-foot rope. We know it weighs 10 pounds overall, and then at the bottom, there's a 2-pound bucket with a 15-pound thing of water. Okay, so let's see if we can sort of analyze how to do this looking at it piece by piece. So let's think about the work for the bucket. So the bucket is a 2-pound bucket. It'll always be a 2-pound bucket. The bucket isn't changing. And that 2-pound bucket needs to go the entire 30 feet. So we should be able to use that basic formula to handle the work for the bucket. So let's go ahead and do that first. There shouldn't be anything fancy here. The work for the bucket, well, it is always 2 pounds, and that entire bucket needs to travel that 30 feet. So the work for the bucket should be 2 pounds times that 30 feet, which looks like the work for the bucket should be 60 feet-pound. Okay, nice and easy. That's one of the 3 things out of the way. Same thing for the water, right? It's a little bit weird to think about the bucket traveling up and then the water traveling up since they travel together. But again, we're just trying to keep the pieces as simple as possible. Notice that the water is always 15 pounds. Things aren't leaking out of the bucket. Things aren't dumping into the bucket. I'm mentioning those because later on we will be able to take examples where the water or the weight inside the bucket is changing. But for right now, it's always 15 pounds. And those 15 pounds of water have to travel the entire 30 feet. So we can calculate the work for the water as the 15 pounds times the 30 feet. And we can see that the work for the water is going to be, 450 feet-pounds. So if we add those together, we know that we have at least 510 feet-pounds of work to do. Okay, now what about the rope? Well, you might say, well, the rope is 10 pounds, so we just take 10 pounds, we multiply by 30 feet. But that doesn't quite make sense, because if you think about it, if you were like a little microscopic being or something and you were on a piece of the rope, well, if you think about it, if you're on this piece of the rope, you only have a very short distance to travel to get to the top. But if you're down here, you have almost the full 30 feet to travel before you reach the top. So in other words, what that means is that each piece of the rope needs to travel a different distance. Pieces at the bottom need to travel almost the full 30 feet, whereas pieces at the top barely need to travel at all. This is why I'm sort of referencing this as the changing distance. Certain parts of the rope have a different distance to travel than others. So let's see how we can analyze that. So what I'm going to do is I'm going to redraw our diagram, focusing now just exclusively on the rope. So we're going to forget about the bucket and the water. We've already accounted for those. So let's go ahead and down here. So we'll just redraw. Let's give ourselves our rope there. And since we're planning on probably having to do something a little bit more advanced, let's also not only just mention the sort of distances, but let's actually define an axis. So what I'm going to do is I'm going to orient my axis facing this way. So I'm going to call the top of the well x equals 0 and the bottom x equals 30. So I'm introducing a variable x here. Could you put 0 down here and go up this way at 30? For sure, you'll get a slightly different expression for the answer, but the overall answer will be the same. The only reason that I'm doing it this way is that this way sort of makes a little bit more sense if we're thinking that we're up here at the top of the well and we're looking down, because we would sort of say, oh, this is 0 from us and this is 30 feet below us. But again, if you want to orient yourself where this is x equals 0 and this is x equals 30, you'll get a different expression, but the same final answer. All right, now what we're going to do is we're going to imagine taking a little cut at some arbitrary x sub I star. And we're going to make that cut of width delta x. So I'm going to cut a section of the rope that is delta x long. So we're taking this piece. And we're going to say that roughly this entire piece, even though it's, the top of it is a little closer than the bottom, we're going to say that this basically all needs to travel together to the top. So in other words, we're going to take this piece and bring it all the way up. So what you can sort of imagine, sort of as I drew my rope here, we're almost taking the rope in pieces rather than taking it all at once. We're sort of saying, let's lift this piece all the way up, then another piece, and putting all those together. The reason that we want to do that in pieces is because it's reasonable to say that everything in this piece basically needs to travel the same amount. Now, of course, this guy is a little bit closer than this part, but again, at some point, we'll let that delta x be infinitesimally small, and we'll sort of smush this together, and then it's reasonable to say it's all traveling the same distance. So let's see if we can come up with the work for this piece of rope. So we're taking just this piece and we're lifting it to the top. Well, as we know, that would be force times distance. So we're still using that formula, but just for this single piece. Well, what is the force, or what is the weight? Well, we know that this is only a portion of the overall rope. Well, what portion of the rope is it? Well, it's delta x out of the fact that it's a 30-foot rope. So as a proportion, we can say that the force here is delta x over 30. That's how much of the rope it is, times the fact that it is 10 pounds overall. So the actual weight of just that little segment is delta x over 30 times those 10 pounds. If you want, you could sort of simplify that and recognize that as 1/3 delta x. If you've taken some physics, you probably know what that 1/3 represents. That's what we call the linear density, because what we're basically saying is if you have 10 pounds distributed over 30 feet, then basically it weighs 1 pound for every 3 feet, or 1/3 pounds per foot. That's exactly what this is saying here. Okay, what about the distance? Well, this piece needs to travel from this xi star to 0. So the distance here is going to be that xi star. So that tells us the work for this piece is actually 1/3 delta x times that xi star, which we can go ahead and rewrite as 1/3 xi star delta x. So that is the work for this single piece to be lifted all the way to the top. That tells us then that the work for the rope overall is approximately the sum of all these pieces. So it's approximately the sum over all those choices of xi star, 1/3 xi star, delta x. Why is it only approximate? Well, because again, technically, by assuming that this all travels xi star, that is an approximation. This part travels a little less than xi star. This part travels a little more than xi star. So again, it is an approximation. How do we make it an equality rather than an approximation? Well, we can say that the work for the rope is equal to the limit as delta x goes to 0 of that xi star, 1/3 xi star, delta x. And we can recognize this now as a Riemann sum because we've got our sum here. There's our delta x, and our delta x is going to 0. So we can rewrite this as an integral. This is the integral. Where can we choose these xi stars? Well, anywhere from x equals 0 to x equals 30. So we've got the integral from 0 to 30. 1/3. This xi star is no longer being chosen. Instead, it's just always from 0 to 30. It's all the values from 0 to 30. So 1/3 x and then dx. And there we go. We've now converted the work necessary for the rope, which has different segments traveling different distances, into an actual integral. Can we do this integral? Yep, should be very easy. This would be 1/6 x squared evaluated from 0 to 30. Plug that in. We get the work from the rope is 1/6 30 squared minus 0. 30 squared is going to be, what, 900? And then 900 divided by 6. Oh, that sounds like 150. So the work for the rope is equal to 150. And, of course, that would be in that foot-pound. So we've handled the work for the rope. And if we look, we can combine that with all these things. So we can sort of put our summary here. The total work is going to be equal to that 60 plus 450 plus 150, which looks like it's 660 foot-pound. So that's the necessary work to lift everything, the bucket, the water, and that entire rope up to the top. Now, before we sort of move on and sort of extend this example a little bit, I want to talk a little bit about some things that would have been different had we changed the axes. If we had oriented our axis this way instead, calling the bottom x equals 0 and the top x equals 30, then notice that the distance would have been measuring from our xi up to x equals 30. So your distance would have been a little different. It would have looked like 30 minus xi star instead of xi star. Then, if you actually try that, you'd still get 1/3 30 minus x in your integral, and you integrate, you get the exact same value. So it's not going to impact the overall number answer. It just impacts what the integral looks like because you're giving yourself a different perspective. The second thing I want to mention from this is that this answer, the 150 foot-pounds, should make some relative sense. If the entire weight of the rope, remember the rope weighs 10 pounds, if it was all piled at the bottom, if all 10 pounds of the rope were at the bottom and it had to travel the 30 feet, well, 10 times 30 would give us 300 foot-pound. But of course, that's way too large because all of the weight of the rope is not at the bottom. It's distributed evenly throughout the whole rope. What did we actually find? Well, we found that it was 150 foot-pound, and that's not a coincidence, as that's exactly half. Because what we were really sort of thinking is, if you imagine sort of weirdly combining the rope, you could take the top half and the bottom half and sort of smush them all in the middle. And then you could sort of imagine that all of the weight of the rope is right there in the middle. Now, that's not a particularly nice way of thinking about it because that doesn't make a lot of sort of physical sense, but that is mathematically equivalent to what we did here. So, again, this gives you guys an example of what we mean by the changing distance. Different segments of the rope had to travel different distances here. Now, let's go ahead and sort of redo this example with an extra consideration. Let's actually imagine now that that water weight that's there is actually changing. So we're going to have basically the same sort of setup, but I want to sort of consider an extra modification here. So now I'm going to call this the changing force modification for work. So we're going to suppose we have the same rope, 30 feet long and weighing 10 pounds. And we're going to further suppose the bucket, weighing still 2 pounds, with water currently inside of it weighing 15 pounds, is still connected at the bottom. But suppose now that you're lifting the rope and the bucket and the water up at a speed at 3 feet per second, but as the water in the bucket is coming up, it fills. So additional water is coming into the bucket at a rate of 1.1 pounds per second. Excuse me. Maybe this is because it's raining outside. Who knows why you're outside trying to lift buckets and ropes and waters out of wells when it's raining. We're not going to get into the narrative of the example, but we're assuming that it's filling at an additional rate of 0.1 pounds per second. So we're going to try to again determine the work necessary to lift the bucket, rope, and water out of the well. Now, immediately before we even do this example, we should intuitively realize that the answer to this is going to be larger than the answer from the previous one. Why is it going to be larger? Because the water is increasing, the weight of the water is increasing, so we're basically lifting something that is heavier. So let's go ahead and sort of draw out our diagram again. So there's our sort of well. There's our rope. We know that the rope is 10 pounds overall. We know that the distance of the well is that 30 feet. We know that at the bottom, there's 2 pound bucket. We also know that there's 15 pounds of water, but we have some additional information. We also know that this thing's going up at 3 feet per second, and we know that the weight of the water is increasing at 0.1 pounds per second. So while this thing is moving up, this water weight is slowly getting heavier. And that's why you can see that this is sort of referenced as the changing force modification, because the weight of this thing, the force necessary to lift this, is changing over time. Well, a lot of the components, though, should stay the same. So the work for the bucket's weight isn't changing. The water is changing. This is why it's good to separate everything into different pieces. The work for the bucket should still be the same. It's going to be those 2 pounds times the 30 feet, which means we're getting 60 pounds. Okay, that part's not going to change. What about the work for the rope? Well, the work for the rope, it's still the same rope. It's still traveling all the way up to the top. So same thing, we would do it as that integral from that 0 to 30 of that 1/3 x dx. And as we saw, that gave us 150 feet-pound. But now we've actually got to investigate the work for the water. And all we would know about this is, my guess is, since this weight is going to be increasing, I certainly would expect that it's going to be greater than what we initially found, which was that 450 foot-pound. But let's actually go ahead and figure out how we could do this. So let's analyze again, just redrawing only the component now that we're focusing on, which is just going to be the water here. So there's our water at the bottom. It's currently 15 pounds, and it's increasing at 0.1 pounds per second. We also know that in general, this thing is being lifted up at 3 feet per second. And we also know, let's go ahead and define our axes. There we go. We'll call this x equals 0. We'll call this x equals 30. Same perspective, so we're looking down this way. All right. Now, are we going to do this in the same manner as the rope? Well, no. It doesn't make sense to sort of cut this and say, well, let's take a piece of the water and raise it all the way to the top. because the water is being treated as a single point. Instead, what we're going to do is we're going to sort of imagine moving this up in several chunks. So in other words, we're going to scoot it up just a little bit, determine the work necessary to raise it just a little piece, and then again, and then again, and then again. Why do we want to do it piece by piece? Well, because the idea is that if we make those pieces very small, if we make the steps very short, then the weight, even though it's changing, won't change that much, and that'll give us a good approximation. So what we're going to imagine is we're going to imagine lifting this thing just a tiny bit up to there, delta x, and then again and again. So we're going to do that, and then that, and then that. So what we want to do is we want to imagine we're at some arbitrary spot, xi star, and we're going to try to determine, each of these is a delta x sort of move. We want to try to determine the work necessary to bring this another delta x further. So we'll sort of state what we're trying to do here. We want to determine the work to move water delta x from xi star. So we know that that's going to be force times distance. So let's think about what we can say about each of those. Well, the distance should be very easy. How far are we going to lift it? Well, we're going to bring it delta x each time, so the distance on each move is just going to be delta x. What about the weight? Well, the weight is going to depend on where we're at. If we're all the way down here, we know that the weight is going to be 15 pounds. But if we're up here, then the weight is going to be different. So how can we determine that? Well, what we can do is we can build a model because we know the weight at the bottom and we can figure out the weight at the top. So let's think about this, right? If, from the information we have here, if we're going up at 3 feet per second, we can figure out that since we've got 30 feet divided by 3 feet per second, we can realize it's going to take 10 seconds to get to top. That should be very clear, right? If we've got 30 feet to go and we're going at 3 feet per second, we've got 10 seconds to get to the top. Since we've got 0.1 pounds per second being added onto the water, we can figure out the amount of water at the top. Water weight at top. Well, what is that going to be? It's going to be the 15 pounds that was initially there, plus 0.1 pounds per second, times the 10 seconds that it's going to take, which is going to be 16 pounds. So we've got 16 pounds at the top. So let's think about those as points. We've got this nice axis, so we can think about this as 30, 15, and 0, 16, right? When x is 30, our water is 15, and when x is 0, our water is 16. But what does this sort of remind us of? Well, we've got 2 points. We can figure out an equation, a linear equation, that models between these two. So let's go ahead and do that. Let's give ourselves a linear model for water weight at xi star. Well, we know it goes through these 2 points, so you can figure out the slope. That would be 15 minus 16 over 30 minus 0, which looks like it should be minus 1 over 30. And then notice that this would be your intercept right there. So we can say that the water weight is equal to minus 130 xi star plus 16. So at any moment, xi star, you can use this formula to figure out the weight. Let's check and make sure if it makes sense. When x is 30, plug that in here. 30 times negative 1 over 30 is negative 1. Negative 1 plus 16 is 15. Good. When x is 0, plug in 0 here. Negative 1 over 30 times 0 is 16. Yep, there we go. Want to know how much water there is when you're at 20 feet in the well? You plug in 20. This tells you how much water is there. So now we know the water weight at any particular moment along the axis. So this gives us our force at any particular moment. So we get minus 130 xi star plus 16. Now, I do want to make one comment here. It might seem weird to you that we have a negative when we know that the water is actually increasing. And again, that's because of our perspective looking down like this. right? The water weighs less at the bottom than it does by the time it reaches the top because it is filling. So again, you got to keep in mind all this is based on the perspective of looking down. So we now know the work necessary to move it one piece, no matter where we're sort of at. So we can do our sort of standard trick. We can say that the total work, so the work for the water overall, is going to be approximately the sum over all those xi star of that -1/30 xi star plus 16 times that delta x. Then we can make that not an approximation by taking the limit. So we can say the work for the water is actually equal to the limit as delta x approaches 0 of the sum over those xi star -1/30 xi star plus 16 times delta x. Okay, now that we have that, we can go ahead and change that into a definite integral. So the work for the water is actually the integral. This makes sense from x being 0 to x equals 30. So the integral from 0 to 30 minus 1/30x plus 16 dx. All right, then we can go ahead and actually integrate that. So we get that the work for the water is -1/60 x squared plus 16x evaluated from 0 to 30. Plug that in, the work for the water, 30 squared, that's 900, divided by 60, that's 90 divided by 6, so I guess 15. So we get -15 plus 480 minus 0, and it looks like the work for the water here is going to be 465 foot-pounds. All right, we can grab that, look back up here, right? If we come back up here, we said it was going to come in greater than 450 pounds. Well, it absolutely did. It's 465, just a little bit larger, because it's not that much water that's being dumped in. It's only 0.1 pounds per second. And if we combine all that stuff together, so our overall work here, well, we know it's going to be that 60 foot-pound plus the 150 foot-pound plus the 465 foot-pound. And that looks like, what? That's 210 plus that 465. So it sounds like 675 foot-pound overall. That 675, you'll notice, is a bit larger than the total we got here, where we got 660, because again, the water weight was increasing over the time here. Okay, so before we call it good for this, we just want to make sure we understand the difference between these two things. So, in these two things, we've took an example. In these two examples, we basically saw an example of what happens when there's changing distance and what happens when there's changing force. Now, something that's very subtle here, and I just want you guys to be very cautious when you're looking over this, is that even though we use the same variable x and delta x, we're doing very different things here. If we look here, the delta x was a piece of the rope. It was the width of the rope. And then we were lifting that entire piece to the top. So we were basically saying, let's take a piece here, lift it up. Let's take another piece, lift it up. Let's take another piece, lift it up, so on and so forth. And once we took up every piece, we combined all that to give us our overall work. So here, the delta x was the width of a piece of rope that we were going to lift to the top. In the second part, the delta x had nothing to do with width, because again, the water is all viewed as being one single point of weight. Instead, the delta x is a movement up. So we are basically moving delta x each time, taking our journey not in pieces all the way to the top, but in one piece, then another, then another, then another, so on and so forth. Basically doing this in a bunch of tiny moves all the way up to the top. All right. We're not quite done with examples for work. We've sort of seen the main ideas here. But in our next video, we'll take a look at another example similar to this, sort of with the idea of what to do with changing weight and changing distance. And then we'll also look at another situation, namely pumping sort of liquids out of containers that can be also analyzed using this definite integral approach.